Hi, I am Sulabh, postdoctoral researcher in Department of Electrical, IT and Cybernetics, University of Southeastern Norway. Today I am going to present the presentation of my paper having title Comparison of Optimal Reactive Power Dispatch Methods in IEEE 30 bus system. This is the outline of my today's presentation, introduction, followed by the objectives and contribution of the paper. Then optimal reactive power dispatch problem with some objective and EBOA algorithm and some case study, test system and result analysis, followed by the conclusion and the references. In this paper, enhanced butterfly optimization algorithm EBOA is used to address the power system's optimal reactive power dispatch problems. IEEE 30 bus network is chosen as a base network to test and validate the performance of the methods. In this system, all three goals, power loss minimization, total voltage deviation minimization, and L-Index minimization are taken into account. And outcomes of EBOA algorithm have been equated with novel butterfly optimization algorithm and additional other heuristics, and also statistical analysis is performed to evaluate the resilience of algorithm. If we talk about the introduction, so according to current power system context, power system operators are concerned with power system security challenges apart from the economy. And voltage security is greatly impacted by reactive power, which is intimately tied to bus voltage. And voltage instability, or in severe situations, voltage collapse can result from an inadequate reactive power supply. Hence, careful consideration must be given to the distribution and management of reactive power. Additionally, many power operators are operating at its full capacity, so there is a chance of component outage when the system operates in an instability area. Hence, the literature survey on optimal reactive power dispatch, it can be concluded that optimal reactive power dispatch is a highly nonlinear optimization problem, and this problem is still open for research. It demands highly robust and intelligent algorithm for its solution, and this can be effectively made possible by metaheuristic algorithm. So optimal reactive power dispatch aims for proper allocation of reactive power from various wire sources present in power systems to attain the security related goals of power system. In this paper, we have minimized the active power losses in IEEE 30 bus system. Also, we have enhanced the voltage stability index and minimizes the total voltage deviation. So optimal reactive power dispatch is a tool for managing reactive power requirements in power system. And purpose of optimal reactive power dispatch problem is to minimize the real power losses, load voltage deviation, and voltage stability index. And it can be ensured by regulating the generator bus voltage, which is continuous variable, and switching on or off SVCs, which is discrete variable. We can also ensure it by changing tap setting of the transformer and regulating other reactive control devices. Here we have make three objective functions regarding the active power losses, total voltage deviation, and L-index. So minimization of active power loss is depicted in equation number 1, and objective function related to load voltage deviation is shown in equation number 2. So, and the objective function related to voltage stability enhancement is given by equation number 3. And after performing the load flow in IEEE 30 bus system, we get the Y bus matrix that is given by equation number 4. These are the variables used in this study. There are some control variables and there are some dependent variables. In control variables, terminal voltage, output of shunt wire compensator, and tap ratio of the tap changing transformer. While in dependent variable, we have considered voltage of load bus, generators reactive power output, and slack bus power. Also, the equality constraints that are given by equation number 5 and 6, and inequality constraints given by equation number 7 and 8 are used in this study. Constraints related to transformers, SVC, and security are depicted respectively in equations 9, 10, and 11. If we discuss why EBOA has been used, so EBOA is recently developed meta-heuristic algorithm, and according to the literature survey, EBOA has not been utilized to solve any electrical engineering optimization problem. Therefore, it motivated me to apply this algorithm in solving complex engineering problems like optimal power flow. The main motive for applying this algorithm is to verify its competency, robustness, and efficiency of the algorithm. And to calculate the global search and local search of EBOA algorithms is given by equation number 14 and 15 here. We can see T is the current iteration number, G star is the current based solution, and Fi is the fragrance of ith butterfly, R is random number between 0 to 1, and Xk of T is the solution of X for kth butterfly with iteration number T. This study we have applied on IEEE 30 bus network. In this bus system, there are 6 generator buses, 24 load buses, and there are 41 transmission line. Total active power load of that system is 283.4 megawatt, and initial losses are 5.81 megawatt. So if in this case study, total control variables are 19, out of which 6 generator voltage, 4 online taps, and 9 var output of shunt capacitor. In this table, we can see that the losses by using EBOA algorithm has been reduced by 22.79%. And in convergence curve, we can see that EBOA has best result than other algorithm. Similarly, for the minimization of total voltage deviation, we can see that the total voltage deviation is minimized by best value with the help of EBOA. Also, for the minimization of L-index, we can see that EBOA has best result as compared to butterfly optimization algorithm and other heuristics. Here we can see in the table that for power loss, total voltage minimization, and L-index minimization, in each case EBOA has better results as compared to other heuristics. So if we talk about the conclusion, under varying degrees of operational and physical limitations, OPF based optimal reactive power dispatch issues are solved using a new meta-heuristic method named EBOA. The outcomes of the simulations and the comparisons with other modern algorithms verify that EBOA performs better in nearly every scenario. Power losses are reduced by 0.76%, bus voltage variation is reduced to 0.61%, and L-index factor is reduced to 0.006%. Further, the robustness of this methodology can be checked on large system, and reliability-oriented network restructuring can be investigated along with optimal reactive power dispatch in future scope of work. These are the references that I have used to make this paper and presentation. Thank you for your patience. For any query, you can contact on the email address